Okay, so in this video we're going to look at electric fields, and here I have two charges, a positive one and a negative one. And if you look at the electric field lines, for the positive one they're moving outward, and for the negative charge, the electric field lines are moving towards the charge. So this is something important that you should keep in mind. And I'm sure we're all familiar with the formula for electric force, right? Kq1 Q2 by R square, where K is the Coulomb constant. Alright, so let's look at electric potential now. So electric potential, this is a very important definition because in IB exams they do ask the definition for electric potential, and if they do, they expect a very precise answer. So it's best to remember this. And this definition tells us that the electric potential at some point is the amount of work done per unit charge. Okay, well, just going off that, we can write electric potential is equal to work done per unit charge. Just like gravitational potential, which is minus gm by r, electric potential is kq by r. Okay, alright, so now we're going to look at electric potential energy. So we've already looked at this formula, right? So just as gravitational potential energy is mass times the gravitational potential, electric potential energy is charge times the electric potential. And this can be simplified into this by just substituting the value of electric potential, the one that we got here. And we also know that like work done is mass times the change in gravitational potential, the work done in terms of electric potential should be this. Now, I'm not sure if you've caught on, but the formula that we wrote here, this formula should tell us that work done is equal to VE times Q. But here, the general formula is actually Q times delta electric potential. And I think this can be explained in terms of what change in something actually means. So suppose we have some point here and another point here. And if I were to say that the electric potential at this point was 0 volts and at this point it was 5 volts, well then what is the change in electric potential? It's just 5 volts. But that's also the same thing as the electric potential here at this point. So in this case, this formula and this formula are both applicable. However, it's always best to remember the formula as delta VE, because if I take this as 3 volts, well, if I move from here to here, VE, I can't write VE as just 5. It's actually 5 minus 3. So while it's been expressed as just VE here, it's important to remember that it is always the change in electric potential. And if we look at this diagram here, we can see a large charge and we have a smaller charge. So this large charge is going to produce some electric field around it. Now let's say I wanted to take this charge and move it like this here. Well, one way to do that would just be to move it in a straight line, right? And then work done would just be Q into this change in electric potential. But I could also move the charge like this and then bring it here. And you would still get the same amount of work done, because at the end of the day, your change in electric potential is going to be the same. Alright, and so I've also written down the definition for electric potential energy. So Now we're going to look at this point here. The electric field strength is the same inside a sphere as it is on its surface. So if we look at the diagram on the left, the graph on the left, if we have a sphere of radius r, well then at this point and everything up until this point, everything up until this distance from the center of the sphere, we're going to have the same maximum electric potential. But as soon as we start measuring distances outside the sphere, which are more than r, in this area, your electric potential is going to decrease in a sort of exponential manner. This diagram on the right is just another way of visualizing what electric potential is. So in the video about gravitational potential, we saw that you can visualize gravitational potential like this right here. But here, this upward bulge represents a positive charge and this downward one represents a negative charge. And the surface that they appear to be manipulating would be the electric field. Now, if I were to take a small point positive charge and put it here, it would act as if I put a ball there. Since there's a hill, the ball would just roll down here. So if I put a charge here, it would feel repulsive forces from this positive charge and it would be attracted to this negative charge, so it would move down just like the ball. Similarly, if I try to push this ball up this hill, it would require a lot of energy. And so if I keep pushing it, bringing it all the way up to the top, it would have built up a lot of potential energy. And what that means is your electric potential is increasing the further up you go. In fact, if you started here and walked around like this, such that you went around, came out this way, and ended up exactly where you started, that line you just walked around would be an equipotential surface. And that's what we're going to talk about next. Now we're going to talk about equipotential surfaces. So what this means is, it's simply a surface that consists of points which have the same potential. So let's say I were to draw a circle. Excuse my horrible drawing. Assuming this was a perfect circle, then if this represented an equipotential surface, well, that would mean that at any point on the surface, the potential will be the same. In other words, if I had a charge here and I wanted to move it from here, point A to point B, the work done would actually be 0 because there is no change in electric potential since it's on the same equipotential surface. So this is kind of why in some cases moving a charge from here to here would simply mean moving a charge from here to here, because this is the change in electric potential that we're going to be calculating. That's all we're going to need. This vertical distance that it travels, this vertical distance doesn't matter, because once it goes here and then it goes up vertically, it's on the same equipotential surface. Okay, so now that we've looked at what equipotential surfaces are, let's really figure out what the connection between potential and fields is. So for this section, I'm going to refer to only gravitational potential, and then we'll also relate it later to electric potential. So we know that work done is equal to change in Vg times the mass. But we also know that work done is equal to force times displacement. Now, force times displacement can be represented like this, where an mg refers to the force and displacement is the change in distance. Now, once we have this, we can equate both of these equations together, and we end up with this. And this is how we relate gravitational fields with gravitational potential. Now, there's something really interesting here, and it's that this is really just an approximation. Because if we were to plot, let's say we plotted gravitational potential with radius here. We know that gravitational potential is just minus gm by r. In other words, it's always negative. And so you'd end up seeing a graph that looks like this. Somewhat like that. And what you find is, if we took 2 points here, here, and here, and let's say we wanted to calculate the gradient. Well, this line in blue would represent the change in gravitational potential. It would be this value minus this value, and then this value minus this value over here would give you the change in distance. And if you do that, what you're really finding is, I'm going to do it in red, what you're really finding is the gradient of this red line and the gradient of the straight red line, or linear red line. So we get a constant value for the acceleration due to gravity, which doesn't seem right, because the graph represents a curve and it shows that at every single point the gradient of this curve, or in other words the acceleration due to gravity, is actually changing. And that makes sense, because suppose this was actually a mass and instead of VE this is VG. Well, if we did the change in gravitational potential from this point to this point and then divided it by this distance r, we'd get a single value for the acceleration due to gravity. But we know that the further away you get from a planet or mass, the acceleration due to gravity should actually decrease. So this value is really just an average. And a more accurate way would be to use calculus to figure out the exact value of g at a certain point. Now, if we look at this diagram on the left, we've drawn both equipotential surfaces, and we've also drawn field lines. And this appears to be a negative charge that I've drawn, because the field lines are moving towards the charge. But there's an important thing to remember here, and that's the field lines must be perpendicular to equipotential lines. And we're going to figure out why. So this is the formula for work done. Now, if we go from some point A to another point on the same equipotential surface, we know that the work done in moving that mass or charge from point A to point B should be 0. Why? Because the change in gravitational potential or the change in electric potential is equal to 0, since it's on the same equipotential surface. But now let's say there was a field line that wasn't perpendicular to the equipotential surface. That means that some component of that field line would move along the equipotential surface. Now, what I mean by component is any kind of vector can always be broken up into its y component and also its x component. It's these components that come together to produce this singular vector. There would be some component that would be along the equipotential surface, which means that there would also be a force. And if there's a force and there is some displacement, then work done cannot be equal to 0. but that defies what should be correct. And that's why all field lines have to be perpendicular to those equipotential surfaces. Okay, now we come to parallel plates, which would be the last topic that comes under electric fields. So let's say I took two metallic plates, one had a positive charge and the other one had a negative charge. Well, we know that the electric field moves away from the positive charges and moves towards the negative charges. So your electric field lines would look like this. Now, an important thing to note is that around the edges of these parallel plates, your electric field lines are going to look a little curved. And it's important to remember that in case the IB does ask you to draw a diagram of parallel plates. Now, we have the electric field. But what is the electric field strength? Well, given parameters like D and given V, which is the voltage across these two plates, you can find the electric field strength is this. Okay, so here we have a hydrogen atom. They're asking us what is the electric potential at a distance of these many meters from the proton. Okay, well, they're basically saying if you go this far away to this point, then any point on this equipotential surface will have the same electric potential, and they want you to find that. Okay, well, let's look at part B. Now, we see that they want you to find the electric potential energy between the proton and the electron if the electron was orbiting at a distance of this much from the nucleus. Okay, well, we know the formula for electric potential energy is kQq by r squared, by r. And well, we have the value of K, which would be this one. We have the value of Q, and the value of capital Q would just be the same as this in magnitude, because protons and electrons have the same magnitude of charge. The R value that we're going to substitute comes from this, and well, that's pretty much it. We substitute all these values in, and we should get the answer. Again, we have to look at the significant figures to make sure we've rounded it off to the right number of significant figures. Yeah, I think this would have to be rounded off to 3.8 times 10 to the power negative 20. And that'll be our final answer. Now, this is, this is potential. It could be electric potential. It could be, gravitational potential. But this is potential, and that's plotted against distance here. So, well, if it was gravitational potential, we know that G is equal to delta Vg over delta R, which means that the gradient of this curve would be equal to G. If this was electric potential, the gradient would be equal to E. And you would see this curve in many questions. So I think it's important to understand how to interpret it. Now let's say they want to figure out the point at which the gravitational, your acceleration due to gravity is equal to 0. And if they do ask that, well, when is this equal to 0? And when is this equal to 0? And that's just, well, the gradient. So, when is the gradient of this graph equal to 0? Well, it's at about this point. It comes close to 0. And so you can approximate and say that it is 0 at a minimum distance of, well, 10 into 10 to the power 6 meters, or well, 10 to the power 7 meters. Another important thing is to look at the notation here. it's given as r slash into 10 to the power 6. What this means is any value that you pick up from the graph, it has to be multiplied by 10 to the power 6. Now, usually in these graphs, you would get better grid lines than the ones I've drawn. They would be more uniform, and you can use them to figure out when the graph is horizontal or when the graph is vertical. Another useful tip is that when the graph is vertical, that usually represents the radius. So the graph is vertical at around this line, which gives you 2. So your radius is actually 2 to 10 to the power 6 meters. So in terms of gravitational potential, this would be the radius of your planet. Alright, so that's all for electric fields. Thank you for watching, and I hope this really helped.